It's time to begin our final unit. And we're going to start by taking a look back at where we've been so that we can see just how far we've come. We started the school year with a zero-dimensional object that we called a point. From there, we put together a whole bunch of points to create lines and segments, even rays, one-dimensional objects. Then we put those together to create two-dimensional objects. Here we have the circle, here we have some polygons, and now finally we're going to put those together, enter the three-dimensional world as we study some surface area and volume concepts. So now we have three-dimensional objects. This has a name. This has a slightly different name. Not talking about their specific names, just the in general name. And that is where we are now. Three-dimensional. We are, of course, needing to keep in mind our properties from the one and two-dimensional worlds, especially those concepts of area. So if you need a refresher on an area topic, you can refer back to one of the earlier videos. We also need to keep in mind our properties from one-dimensional objects. All that stuff now comes together for this final unit. We're going to start with some vocabulary to get us going. Any three-dimensional shape can be given the term solid. Just like any two-dimensional object can be given the term shape. Shape is usually a two-dimensional object that could be a polygon. We know that circles cannot be polygons, so we need a term for that, and the term often is shape. Well, we know that spheres and cylinders and cones all have some kind of curvature, so we cannot call them by our next term, so we need a more generic term, and that generic term is solid. Here's our more specific term for solids that are made up of only polygons, and we call that a polyhedron. Polyhedron. Here are some examples of some figures. The one on the far left, we can call a solid. In fact, all of these are solids. The only one that gets to be called a polyhedron is the one on the far left, made up of all of these polygons put together. There are 6. I have 6 parallelograms that fit together to create this polyhedron, made up of polygons. It is a solid, it's also a polyhedron. Here we have a solid, more commonly referred to as a sphere. Like a circle, it has no straight parts whatsoever. It is constantly curved throughout. This solid has a polygon here. It has a polygon here. Has a polygon here off to the side, but then it's got this curved shape on the end. That is not a polygon because of that curvature. So therefore it cannot be called a polyhedron. It's just a solid. Same thing with this. We have a polyhedron almost, but it's got this hole drilled all the way through. That makes this shape with this little hole right here not a polygon. No polygons have holes punched in them. So this cannot be a polyhedron. It is just a solid. Really, the only difference between the two terms is strictly made of polygons only. And there is a site, don't want to take you there. I will do that later. I have to stop this in order to access that. I will have a link to a website that has hundreds of different types of polygons and all sorts of complexity and various types and really, really long named shapes and solids, all sorts of things to play around with. I will include a link for that along with this video. Lots of really cool things to explore there. You can see polyhedrons that are made up of 78 individual polygons. A couple even go over 100, and some have what are called stellations, which means star patterns, and all sorts of really odd and strange things going on there. So I will link to that in this description. Here are two polyhedrons. And we'll get more specific names a little later. For this first introductory lesson, I just want to get through some of the basic vocabulary so that we have an understanding of what things are called and how things relate to each other. So every polyhedron has three basic components. It has what are called faces. It has what are called edges. And it has what are called vertices. Vertice being the plural form of vertex. So on each of these figures, I will point to an example. A face is simply one of the polygons that make that solid. If you think of a room that you're currently sitting in, one wall of that room is a face, assuming that the room is not curved. Most rooms typically have 6 faces. There's a floor, there's a ceiling, and there are 4 walls. Assuming that the door and the windows are not there, that room would be a polyhedron. 6 faces, six rectangles. The floor and ceiling are most likely rectangular. Each wall is a rectangle. You have a total of 6 faces. This figure on the left has a total of 7 faces. You have 5 walls going around. You have the floor and the ceiling that are each pentagon shaped. These walls are each parallelogram. So total of 7 faces. The one on the right has 8 faces. 4 triangles going around here, 4 triangles going around here. This one does not count because it's entirely inside. If we were to drop this in a big container of paint, this 4-sided shape would not get painted. It is not a face. It is simply just created by all 4 of these sides coming together. But it is not a face of the polyhedron. So this one has 8 faces. Edges. An edge in the 3-dimensional world is just one of the segments of one of the polygons. A segment is referred to as a side, typically, or a measurement. In 3D space, we no longer call this a segment, we call it an edge. Same concept, different name. So let's count the edges. This is a pentagon, so this has 5. This has 5, so we're up to 10. And then we have 5 connectors connecting floor and ceiling. So there are 15. This one over here has 4 going around, and then there are 4 connecting this to the top, 4 connecting that level to the bottom. So there are 12 edges total. And then a vertex. Vertex is just where 3 edges come together. In a polygon, 2-dimensional world, let's go back there for a moment. Back to this 2-dimensional world. This vertex has 2 segments. This vertex has 2 segments. This vertex, 2 segments. Every vertex has 2 segments that come to it. In the 3-dimensional world, every vertex has 3 edges that meet there. Every vertex deals with 3 edges. Same thing here. Only, this vertex has 4 edges. 4 edges. What's the difference between the 2? Well, here we have what's called a prism. And we'll talk more about prisms in a later lesson. Here we sort of have a double pyramid. And the effect there is there's a vertex where a lot of these edges come together. So we have different rules for vertex for different solids. Typically, with a prism, you will have 3. Once you get beyond that, you could have sort of any number. This vertex has 4. This vertex has 4, and so on. But usually you get a consistent pattern. So every vertex here has 3 edges. Every vertex here has 4 edges. Let's count the vertices. There are 5 here. There are 5 here, giving us a total of 10. Looking at this figure, I've got 1 vertice, 4 here, and another 1 here. There's a total of 6. Faces, edges, vertices. Every polyhedron has those 3 things. There's a relationship between those 3 items. Take a look at our 3 values here. 7, 15, and 10. 8, 12, and 6. Notice these 2 values right here and these 2 values right here. If you add those together, they're 2 more than the number of edges. The number of faces plus the number of vertices will equal the number of edges plus 2. This is sometimes called Euler's formula. It's not Euler, it's pronounced Euler. Named after the mathematician Leonhard Euler, who was the most prolific mathematician that has ever lived. If you put together all of his writings, currently it would fill about 77 volumes. There is very little that this individual did not write a paper on. In terms of just sheer quantity of work, no one has done better than him. the vast majority of the things that he created are just mind-boggling. Many things are named after him. He discovered all sorts of formulas. He sort of found better ways to do things that were already known. There is very little that he did not put his hands on. Created a lot of original work as well. This particular formula is one that was sort of known before him, but he was the one that actually proved that it was true. And it is true as long as a polyhedron does not have any holes punched in it. If you start punching a hole into a polyhedron, you are adding faces and edges. And there's another factor that you have to take into account. We're not going to worry about that. But if you ever take a course in higher level geometry someday, you might get to see some of those things. Euler's formula can be used for solids that do not have holes. So if we were to punch a hole into a solid, like this one here, for example, we would have some trouble. We would have to alter Euler's formula somewhat to account for that hole. This problem also, we would have to make this some sort of polygon, not a polyhedron. I'm sorry, not a circle. This could be a rectangle, square, hexagon, octagon, whatever polygon we could put here. The point is it would have to be all segments. So we would have more edges, more vertices on either end. We would have had more faces and so on. And then we would have to alter Euler's formula a little bit. So that is sort of our polygon introduction. Sorry, this is our polyhedron introduction.